course BSc, subject nuclear physics, chapter number 1. This is part 3 of this video series. The topics which has been covered in this particular video are nuclear energy, mass defect and the packing fraction. My Facebook ID is www.facebook.com/apniphysics. Web address for this such kind of video lectures you can visit anytime, www.apniphysics.com. Myself, Dr. Sushil Kumar. The first point is about the unit of energy. Here the unit in which nuclear energy is expressed is called the electron volt. As you know that in classical mechanics you observe the energy in joule, right? And in atomic physics you have seen that in electron volt, and then after in kilo electron volt, and now in nuclear physics we measure it in mega electron volt. So basic unit for this energy we use in electron volt. What is the electron volt? What is the definition? How to define it? So for the definition we define electron volt is the amount of energy acquired by an electron when accelerated through a potential difference of 1 volt is called an electron volt. So electron volt is what? Electron volt is the acquired energy by an electron when it is accelerated through a potential difference of 1 volt. So this is simply the definition of the electron volt, which you can see here. That is E, that is charge of the electron. V is the applied volt, that is the 1 volt. So charge of the electron, you know, that is 1.6 into 10 raised power minus 19 coulomb, and volt is the 1 volt. When you multiply 1 electron volt is equal to this 1.6 into 10 raised power minus 19 joule, right? So if you have to convert electron volt into the joule, then you have to multiply it with this factor 1.6 into 10 raised power minus 19. The bigger unit of nuclear energy is mega electron volt. As such we use mega electron volt for the nuclear energy, and that is equivalent to the 10 raised power 6 electron volt. Now the second point, relation between the atomic mass unit and energy, right? Atomic mass unit is to measure the mass of the basic constituents of atom. So according to the Einstein equation, we know that energy one can define with the mass in multiply by square of the c, that is speed of light. M is equal to 1 atomic mass unit is equal to approximately 1.66 into 10 raised power minus 27 kg. We have already determined this value in earlier video. Now by putting the value of c, E, and we get this capital E is equal to 931.49 MeV. In general we use 1 atomic mass is equal to 931.5 mega electron volt. So 1 atomic mass unit is equal to 931.5 mega electron volt generally we use in numerical calculations. Now the next point is about, after the energy definition, the properties of nucleons with different mass scale is used. So here you can see the proton and the mass of that in kg, that is 1.6726 into 10 raised power minus 27 kg in terms of atomic mass unit. In terms of mass, that is basically mv upon c square, right? So mass here E upon c square, that is 938.28 for the proton. Charge on the proton is +1. Neutron mass is 1.6750, that is greater as compared to the proton. and here it becomes in atomic mass unit, that is 1.008665 939.57 in terms of the mega electron volt, and charge is 0 on the neutron. Similarly for electron, mass is 10 raised power minus 31 order, and here in atomic mass unit 5.486 into 10 raised power 4 minus 4, and this is 0.51 mega electron volt, and charge is -1. And then after hydrogen atom, and its mass in kilogram atomic mass unit and in mega electron volt. Right, now the second part is about the nuclear size. As you know that to determine the nuclear size, one use the this simple volume formula of the spherical nucleus, keeping in mind that nucleus is spherical, so volume is proportional to the total number of nucleons. Right, by using this factor here we observe that R is directly proportional to A raised power 1 by 3, where R is equal to R naught into A power 1 by 3. R naught is the constant. That value basically we consider in general 1.4 Fermi. 1 Fermi is equal to 10 raised power minus 15 meter. So nuclear diameter we know that is 10 raised power minus 15 meter, and atomic diameter is equal to 10 raised power minus 10 meter. Right, so these are some basic points about the nucleus. Now the next part is about the nuclear density. Here this profile is basically, which is plotted, represent the nuclear density of this 59 cobalt and 197 gold. So here on y-axis you can see the nuclear density, that is represented by rho, nucleons per cubic meter, and this is radial distance on the x-axis. This is radial distance in terms of the Fermi. Right, so here if one have to determine the nuclear size, there is this is one of the method, and second method is by using this density profile. So nuclear radius, basically as you know that nuclear density is not uniform throughout the radius, it is maximum at the center, right? So nuclear density is maximum at the center, and then after it gradually decreases. So density distribution is not uniform, right? So it is maximum at the center of the nucleus and falls as we move from the center to the boundary of the nucleus. And second point is that nucleus has not well defined boundary. Radius r of a nucleus has also been defined as the distance at which the density of nuclear matter falls to 1/2 of its maximum value. So maximum value is suppose this one, so half of it is this one approximately. So where this line cut, that distance basically on x-axis is the r naught. So this is the nuclear radius for this particular nucleus, and similarly for the next one. So approximately these are the nuclear radius. So one has to determine, if suppose the nuclear radius by using the density profile, then at the half of the maximum value, that is the nuclear radius, which cut it at half, and then this particular distance on x-axis is known as the nuclear radius. The nuclear density, as you know, the basic formula of density is mass per unit volume. Density we define as mass per unit volume. So if we have to find out or determine the nuclear density for any nucleus, then we have to calculate the mass, or we have to observe, or we have to find out the mass of the nucleus and the volume of the nucleus. So then after one can find out the density of the nucleus, right? So in the last slide you have seen the density profile. On x-axis we have defined here radius, and on y-axis that was the rho is the density of the nucleons. So here you can write nucleons per cubic meter. This is on y-axis, right? And the behavior of it was like, and radius we have determined that this is the maximum value of rho at the center, right? So half of it is suppose this one. So where this cut here at this particular point, if you draw a perpendicular on x-axis, so this distance is known as the radius for that particular nucleus, if one have to determine the value of nuclear size, right? But right now the point is that we have to determine the value of nuclear density by using the mass per unit volume. So the mass of each nucleon, we know that whether that is proton or neutron, is approximately 1 AMU. Mass of each nucleon, that is 1 atomic mass unit, is equal to 1.66 into 10 raised power minus 27 kg, right? And mass of the nucleus, let me know what do you think now. What will be the mass of the nucleus? If suppose you have atomic mass number A, element X, Z is the proton number, N is the neutron number. So mass of the nucleus, how many nucleons are there into this particular nucleus? A, right? How many nucleons? A is equal to Z plus N. So one nucleon have mass is equal to 1.66 into 10 raised power minus 27 kg, and if there are A nucleons, then total mass of the nucleus will be A into 1.66 into 10 raised power minus 27 kg. So this will be the mass of the nucleus, capital M. And now volume of the nucleus, that will be equal to the, keeping in mind that nucleus is spherical, that will be 4 by 3 pi r cube, where r is the radius. We have mass that is equal to A into 1.66 into 10 raised power minus 27 kg, and volume is equal to 4 by 3 pi r cube, right? So as you know that r is the radius, nuclear radius, so this can be defined as r is equal to r naught a raised power 1 by 3, where in general r naught we use 1.2 to 1.6. so I am taking here 1.2 into 10 raised power minus 15, right? So now putting these values in the above formula, rho becomes A into 1.66 into 10 raised power minus 27 kg, and divided by this 4 by 3 and this pi, r cube is equal to r naught cube, that is 1.2 into 10 raised power minus 15 meter cube, right? And multiply by, right, so this is A cube, A into A, because this is cube of r is equal to r naught a raised power by 1 by 3, so here you will get only the A. This A cancel out, this A cancel out with this number here, and when you will simplify the result, it basically comes approximately 2.3 into 10 raised power 17 kilogram per cubic meter. So this was the unit of the density, nuclear density rho. So rho is equal to kilogram per cubic meter, right? And this rho is approximately of the order of 10 raised power 17, right? Now you know how much density will you expect for the atom. As you know that atomic radius is 10 raised power 4 times the nuclear radius. Yeah, you know that 10 raised power minus 14 meter is the radius of the nucleus, and 10 raised power minus 10 meter radius is for the atom, for the nucleus, and this is for the atom. So the difference is of the order of 10 raised power 4 atomic radius, right? So this is atomic radius, 10 raised power 4 times nuclear radius. Yeah, so now if you put all the value, you can find out the atomic radius and atomic density, and that is 2.3 into 10 raised power 17 kilogram per cubic meter divided by the volume of the atom, that is 10 raised power 4, and this is cube, approximately 10 raised power 2.3 into 10 raised power 5 kilogram per cubic meter. What is mass defect, right? Here you know the atomic mass and mass of the nucleons. So now we will define the mass defect. You know that nucleus is formed when proton and neutrons are brought close to each other, right? They together form a nucleus. So nucleus is made by the nucleons, that is neutron plus protons. When these nucleons brought close to each other, then nucleus form, and it is found that mass of the nucleus, it is found that mass of the nucleus is always less than the sum of the constituent neutrons and protons. Mass of neutrons and protons, sum of these. So mass of the nucleus, if suppose Mn, so right, mass of the nucleus, and mass of the neutron and proton, here one can write for Z for the proton, mass of the proton, 1 proton plus n total number of neutrons, and multiply it by 1 neutron mass, right? So Mn is less than the sum of these constituents mass of the nucleus. So the difference between these two masses of the nucleus and the sum of these constituents, that is known as mass defect. So mass defect delta M is equal to the ZMP plus NMN. This mass is larger as compared to the actual nucleus. So the difference between the Mn is the mass of the nucleus. So this difference is known as mass defect, right? So delta M is equal to this mass of the nucleus constituents. This is Z for the proton number, this is N for the neutron number, MP mass of 1 proton, Mn mass of 1 neutron, and you can define N here, that is A minus Z. So sometimes one can write in this way also. So this is the mass of all the neutron. Mass of all neutrons which are available into the nucleus. So this is simple definition of the mass defect, and further we will discuss about the packing fraction.